Now let's try to understand how using one or more predictors, the factor which we have so far been calling exposure variable, are used to estimate the response, which we have so far been calling outcome variables, using regression line and regression equation. First, let's try to refresh our understanding of the regression equation that we learned back in our high school math. Y in the regression equation is the estimated response. It represents the predicted value of the outcome. In our example, it is the estimated systolic blood pressure based on BMI. Beta naught is the intercept. It is the starting value of the outcome when the predictor is equal to 0. In our example, it would be the systolic blood pressure when BMI was equal to 0. Please note that this is a theoretical value. No one can have a BMI is equal to 0 or a cholesterol is equal to 0 or height is equal to 0 because it has no real world meaning but provides a mathematical starting point. Beta naught is what we call the slope. This is the most important part of the regression. It represents the predicted change in the outcome for each 1 unit increase in the predictor. The example could be a change in systolic blood pressure for every 1 unit increase in BMI. This is what the statistical software calculates for us. X1 is the predicted unit, 1 unit of the predicted variable in the calculation. An example could be 1 BMI unit or 1 milligram of cholesterol or 1 cigarette per day, etc. Now let's look at how regression helps us estimate a response, in this case systolic blood pressure based on predictor BMI. We'll go through 2 examples. One, when there is no association between BMI and systolic blood pressure, and number 2, when there is an association. First, consider this example of no association. Here, even as the BMI increases from 20 to 25 to all the way to 40 across different participants, the systolic blood pressure stays the same at 120 millimeters of mercury. Now let's plot this data. As a BMI increases from 20 all the way to 40 across participants, systolic blood pressure remains constant at 120 millimeters of mercury. The first participant with the BMI of 20 right here had a systolic blood pressure of 120. The second participant with a BMI of 25 had a systolic blood pressure of 120, and so on. So when we join these red dots, the result is a flat horizontal line. The slope is 0, meaning that there is no change in systolic blood pressure regardless of changes in BMI. If we extend this line back to BMI 0, the intercept is also 120 millimeters of mercury. We call this intercept as beta naught. So this flat line tells us clearly that there is no association between BMI and systolic blood pressure in this example. And if we use all the values which we saw in our graph, we'll see that in the equation, in the scenario, all participants have the same systolic blood pressure regardless of BMI. Therefore, the slope beta 1 is 0, and the regression equation looks like something like this. Systolic blood pressure is equal to the intercept, which is 120 millimeters of mercury, plus 0 times BMI, meaning that if we plug in the value 20 or 25 or 30, the systolic blood pressure of all the individuals will stay the same, that is 120 millimeters of mercury. And our interpretation would be something like this, that a slope beta 1 of 0 indicate no relationship between BMI and systolic blood pressure. Thus, changes in BMI have no effect on systolic blood pressure. Now let's look at another example where there is an association between BMI and systolic blood pressure. We see that participant 1 has a BMI of 20 and a systolic blood pressure of 120. Second person has a BMI of 25 with a systolic blood pressure of 130. Third person BMI 30, systolic blood pressure 140. Then BMI 35, systolic 150. And the last person has a BMI of 40 with a systolic blood pressure of 160. So if we plot these values on a graph, the first person with a BMI of 20 and a systolic blood pressure of 120 will be represented by this dot, second person by this dot, and then so on. And if we connect all these dots, we get a straight upward sloping line like the one you see on your screen. And if we extend this line further backward, it connects to the vertical axis at 80 millimeters of mercury. All right. This represents the theoretical blood pressure when the BMI is 0. That point is called the intercept or beta naught, which in this case is 80. It is in fact the baseline or the starting value of systolic blood pressure at BMI 0. So looking closely, for every 5 unit increase in BMI, systolic blood pressure rises by about 10 millimeters of mercury. That means the slope beta naught is 2. So for each 1 unit increase in BMI, there is an associated almost 2 millimeters of increase in systolic blood pressure. Plugging these values in the regression equation, we get systolic blood pressure equals 80 plus 2 times BMI, where systolic blood pressure is the estimated response based on our predictors. 80 is the beta naught, the intercept, the theoretical starting value for systolic blood pressure when the BMI is theoretically 0, and 2 is the slope, which indicates that for every 1 unit increase in BMI, systolic blood pressure rises by 2 millimeters of mercury. For example, for a person with a BMI of 30 units, the systolic blood pressure is predicted to be 80 plus 2 times 30, which comes down to 140 millimeters of mercury.